In the first part, I implement the CGFX shader through Shader Toy.
In this demo, we can see a real-time rendering of the scene based on ray tracing technology. The scene consists of a sphere and a plane. Through the ray tracing algorithm, we are able to calculate the color of each pixel, achieving a highly realistic rendering effect. Next, I'll explain the code for this ray tracing shader in details.
First, we define the maximum number of iterations, maximum distance, and surface accuracy, which determine the accuracy and performance of ray tracing. Next, in the getDist function, we define the objects in the scene, including a sphere and a plane. Through this function, we can obtain the shortest distance from any point to these objects, which is a key computational step in ray tracing. Then, in the RayMatch function, we perform the actual ray tracing. The function calculates the distance of the light in the screen to determine if the light intersects the object, and calculates the location of the intersection point. And then we define the getNormal function, which computes the normal vector for a point in the scene. The normal vector is very important information in the ray matching, which determines the reflection and illumination effect of light on the surface of an object. In this function, we use the small offset and the getDist function to calculate the normal vector around the point. Finally, we define the getLight function, which is used to calculate the light intensity. In this function, we define a position of the light source and the direction of the light. Then we calculate the distance from the point to the light source. Through the method of ray matching, judge the shadow and finally get the diffuse reflection light intensity. This function gives the image a realistic light and shadow effect by calculating the illumination of points in the scene. Finally, in the main-image function, we set camera and light. We transmit light from the camera to each pixel on the screen and calculate the corresponding color. In the end, we get a realistic ray matching rendering.
In part 2, I made a lava PBR shader to implement random effects. Here I use noise function to create natural random textures that simulate irregularities on the magma surface. This function can generate numerical values with a random quality that are used to create changes in colors or normals on texture coordinate. In this shader, the smooth step function can be used to control transitions of colors, normals, or other properties, resulting in soft transitions between colors or textures that avoid hot edges and increase visual comfort. Also, the vertex normal WS can achieve the effect of photorealistic illumination. By mapping the normals to world space, shader can calculate the illumination effect more accurately, making the surface of the magma more concave and convex. We can implement opacity and specular through this shader. Here, we can choose different types to change the texture. Other nodes are similar with before. Here, we can change colors. Also, we can change the properties by changing different values. Now we set the opacity value to 0.5, so it will be translucent. If we set it to 1, it will be opaque. In this shadow, emissive strength is used to control the self-illuminous effect of objects. By adjusting this property, we can determine how much light an object emits in a low-light environment, making it appear that the object is shining. Fresnel is often used to adjust the reflection of the edges of objects. The edges will be more susceptible to ambient light, creating a bright edge effect. Fresnel random color refers to the introduction of random colors based on the Fresnel effect, so that the reflection effect of the edge part will show random color changes. Opacity is usually used to control the transparency of an object. The value will change between 0 and 1. Now here is a raindrop PBR shader. We can see the surface is falling rain. The right side is event graph, and I will deconstruct the PBR shader from the following 4 aspects. Here we can change different textures to change the surface. In PBR shader, normal nodes are often used to simulate the concave and convex view of the surface, making the lighting effect more realistic. In this raindrop PBR shader, normal nodes can be used to produce a bump texture of water droplets on the surface, making raindrops look more three-dimensional and natural. Normal mapping can give each raindrop unique normal information based on the position and direction of the drop in order to produce the right reflection and refraction effect in light. Then we can make raindrops slide on the surface at a certain speed to create the effect of water flow. This dynamic effect can be achieved by modifying the UV coordinates or the displacement texture coordinates so that the raindrops appear not to be stationary but to flow across the surface. Static effects can be used to simulate raindrops that have accumulated on the surface. By adding a raindrop texture to the surface of a static object, it can be made to appear that the raindrop has stayed on the surface rather than constantly falling. This effect can be achieved through texture mapping or material properties. We can control the falling direction of the raindrop and control whether it rains or not. By controlling the falling direction of the raindrop, it can form different patterns on the surface, increasing the customization of the raindrop effect. This parameter can be used to dynamically control the raindrop effect on and off so that the weather effect can be changed at any time when needed. Here we can change the color of the surface to any color we want.